Okay, so here is how I would do this problem. Now, we know that we begin with a box, a cube, if you will. So we begin with a cube, and the dimensions of the cube are x's all the way around, which is why the volume is x cubed, because for a box or a prism, how do you find the volume? You go length times width times height. So for this, pretend this is a cube here, because it almost is, sort of. The volume of this would be the length times the width times the height, these three dimensions. That's how you find the volume. But what's gonna happen is we're gonna take our cube and we're gonna stretch it out so that the cube becomes more like a rectangle. So what I want you to see is before, this dimension we called x, like right there, x. But what's gonna happen is this dimension, it's gonna be stretched and pulled out so that, for instance, this part here in the bottom, it becomes this part here. So if you call this x, you cannot call this x because more than likely, this is bigger than that. So here's what I'm saying. Why don't we draw a rectangle, and I'll draw another rectangle sort of inside of it, and then I'll connect the adjacent vertices so as to draw a rectangular prism. So what I'm saying is this: before we called this x, but it got stretched out to something different. So what I'm gonna do is I'm gonna call this x plus, I don't know, how about a? If you just pick a letter from the alphabet. Now how about this, watch. So that was the previous base, or the length, that was the length. Now let's talk about the width. What was the width called before? It was also called x. But now the new width is this one here, and I don't know what this is. So I can't call it x. Instead, I'll call it x plus b. Now, the original item had a height of x, but now I don't know what the new height is, right? I mean, these objects are just random. They don't actually represent the problem. It's just here for illustrative purposes. So before, this was called x. So here, since this is probably different, I'll call it x plus c. Now, this is a rectangular prism, a box. How do you find the volume of a box? You go length times width times height. So I know that for the volume of this solid, it's got to be length times width times height. So I have to go x plus a times x plus b times x plus c. Why did I choose a, b, c? Because they're easy letters to play with. You could pick any three letters that you want. So here's what I'm going to do. I'm going to multiply this out. So I'm going to look at these two pieces first, and let's see what happens. So let's do this here, which is called the distributive property. So let's see. X times x is x squared. X times b is bx. A times x is ax, and then a times b is ab. Keep that in parentheses. And we still have to multiply it with x plus c. So now let's distribute again. So how about I take the x and I distribute just the x for now. So let's see what this gives us. So x times that is x cubed. X times this is bx squared. That and that is ax squared. And this times that is abx. And now, similarly, why don't we distribute the c? So let me take this one and distribute there, 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 and there. And so c times that would be cx squared plus that times that would be bcx. You could always like switch the letters. That times that is acx, and this times this is abc. Now look, I always tell my students to keep track of what the goal is. What are we trying to do? The directions want us to give them the dimensions of the new shape. So we want to know these dimensions here. So we're trying to find a, b, and c. Let's do some more math. we'll discover A, B, and C. We'll call this the length, we'll call this the width, we'll call this the height, and we get our A+. So now what I recommend that we do is look at all these pieces. Some of them have exponents, some of them have variables, some of them don't. Let's group them strongest to weakest. The strongest piece is this one because it has the strongest exponent. Now let me write down all the pieces that have x squared. And now let me write down all the pieces that have just a regular x. For example, this piece there, and this piece here, and this piece here. And then what's left to write down? The only piece left to write down is the last piece because that has no variable, no x variable. Now here's what I would do. If you look at, this is just x cubed, so that stays the same. Now, if you look at these pieces here, what do they all have in common? What is their greatest common factor? Their greatest common factor is x squared. So what I'd like to do is I'd like to do this. I'd like to take the x squared and pull it outside to the back. And then what would be left inside? Just the b plus the c plus the a. And if you want to alphabetize, that's totally fine. So hopefully you guys discussed in class the idea of factoring out a GCF, which is exactly what I did. Now, similarly, if you look at these pieces here, what do they all have in common? What can you take out of all of these pieces? You can take out x. And I'll do that, and I'll deposit the x just in the back. What would be left inside? AB plus BC plus AC. And then just this piece in the back here, like that. Now, believe it or not, we're actually getting somewhere. We're almost done. We really, really are. Now, here's what I want to do. Remember, in the original problem, they told us what the volume equaled. They said, hey, the volume of the new shape is x cubed plus 6x squared plus 11x plus 6. So this is the volume that was given to us for free. But you and I did the same thing using a different technique. But our answer represents the volume, and so does their answer. So whose answer is better? No one's. They're the same. So what I'm trying to get at is that we can create an equation that says this volume is equal to this volume because they are each the volume of the same object. So down here, let me create an equation that says this equals that. Here's what I want you to do. I want you to make a comparison between the left-hand side and the right-hand side. This is an equation, and right now it is perfectly balanced. Is there something on this side that you see can knock out something on this side? If you notice, there is an x cubed and an x cubed. So we can subtract x cubed from both sides, so they essentially eliminate one another. So they're gone. Now, for the rest of this problem, I want you to make a comparison. Realize that this left equals this right. So the pieces from here have to match perfectly with the pieces from here. For example, you know how this says x squared? You know how this says x squared? By comparison, we can say that this piece has to equal this piece. They have to match. X squared matches perfectly with x squared, which means that this coefficient has to be equal to this coefficient. So there is an equation that we can create, and that equation would say this. It would say that 6 equals A plus B plus C. Check this out. How about this one in pink? This piece called 11x, that has to equal this piece here. How come? Because that has x and that has x. And that means that 11 has to equal all of that. And of course, finally, this means that 6 has to equal A, B, C. So we can say that 6 has to equal A times B times C. We have just created what they call a system of equations. So we need the numbers A, B, and C so that we can plug them there, there, and there. And these three pieces is the answer. So looking at this system of equations here, can you look at it and maybe guess and trial and error? Can you find the values of A, B, and C? One way of solving this system of equations is by trial and error, just experimenting with the numbers to make them work, to make them fit. I think that for a problem like this, they'll give you numbers that are kind of small. So I'm just going to tell you what they are, and then you can see why they work. I propose to you that the numbers that work here are 1, 2, and 3. But which one's which? Well, in the directions, they did want the length to be the biggest. So I'm going to let A be 3. And then 2 and 1 can go to either one. It doesn't matter. I'll just call it like this. And let me prove to you that these are legit. Let's plug these numbers into the top equation. How much is A plus B plus C? Well, 3 plus 2 plus 1 is 6. How about the bottom? A times B times C. How much is 3 times 2 times 1? That's 6. How about the middle equation? How much is A times B? A times B is 6 plus, how much is B times C? B times C is 2. And how much is A times C? A times C is 3. And how much is 6 plus 2 plus 3? 11. So these numbers work. So what I'm saying is up here, that x plus A is really x plus 3, because that's what A is. And then here, that's really x plus 2, and this is x plus 1. So the final answer, after all of this math, the new length should be x plus 3. The new width should be x plus 2. And the new height should be, what does it say? It says x plus 1. Now look, is there a faster way of doing this? Maybe. I don't think so. But I propose to you that this is one way of doing a really fun problem like this one.